Good afternoon, everyone, and welcome to another ISCFD webinar. We're very pleased today to be joined by Professor Matthew Juniper from Cambridge University. And just a quick bit of housekeeping before we begin with the session. So, as you've heard many times in all of the other webinars that you've been to, you're going to be muted. Please respect that. We will be recording the session today, so it's going to be available at a later stage in case you didn't catch something. And if you do have any questions, please post them in the chat, and then at the end, after about 45 minutes, when Professor Juniper is finished, we'll have a sort of 15-minute Q&A where you can engage and ask any burning questions that you have. So we're very grateful that Professor Juniper has joined us. He is, as you may know, a very recognizable name in the fluid industry. He is the head of the UK Fluids Network. He is an associate editor in the Journal of Fluid Mechanics, and he has spent many years as a researcher at Cambridge University, and is in general a very talented and successful scientist. We contacted Professor Juniper several months back to ask to give a webinar, and he said just wait a little bit, because we're working on something and it's going to be finished soon. And in fact, this research that he's about to present to us today concerning the Inkjet Printhead, which to me sounds absolutely fascinating, was presented at the American Physical Society conference just this week. So it's very fresh research, and we're all very excited to hear about it. So again, thank you to Professor Juniper, and thank you to you all for joining today. And Professor Juniper, I will hand the floor over to you.
Great. Thank you very much, Jamie, for a very kind and totally undeserved introduction. Thank you. I'm going to start. There are sort of 6 parts to this talk. I'll start with a simple introduction to adjoint methods, which I expect many will have heard about, and I'm going to do a sort of philosophical introduction rather than a technical introduction. I'll then talk about how an inkjet printhead works, and that'll be very basic, but just to get the basic ideas across. Then, because this is a CFD group, of course, I'll give some information about the governing equations and the solver we use, which in this case is finite element. I'll talk then about a project we did on shape optimization. This was actually about a year ago we published that. And it leads us into then this new project, which is on the actuator waveform optimization. That won't make sense until I talk about how an inkjet printhead works. And I should say that this work was done by, what's going on here? There we go. By Peter Kungertsev, who was a PhD student who's just finishing writing up. He's due to hand in about 2 weeks' time, and was funded through a Marie Curie ITN. And that's me on the right. So then we'll start with this very simple sort of philosophical introduction to adjoint methods. So let's imagine you had an airfoil like this, and you could define its shape in 2D by these points, and these points have an X position and a Y position. So if you had 50 points, you'd have 100 parameters that define the shape of the airfoil. If you wanted to work out the lift and drag, for example, you might mesh around the airfoil, and then you have, of course, many more degrees of freedom on the mesh. You then calculate things like, well, the flow variables, things like U, V, W, the 3 components of velocity, and the pressure, if it was an incompressible solver, around on the grid. And then afterwards, you would work out the quantities of interest, which would, for example, be lift and drag, or lift over drag, say, whatever it is. So what I've done now is I've represented this in terms of degrees of freedom. So we start off with, on the left, I've shown 25 dots, but if you get the feeling there's sort of roughly 100 degrees of freedom define the geometry, each of them represented by a dot. The next stage, when you work out the flow variables on a grid, now here you have an enormous number of degrees of freedom. I've written down 10 million, but depending on the size of your calculation, it might be 100 million. It could be 100,000. The point is, it's many, many more than the number of parameters that you have. So you go from, say, 100 parameters to, let's say, order 10 million flow variables. And what you do next is you work out U, V, W, and P, integrate the pressure, for example, around the shape, and take its components in the lift and in the horizontal and vertical directions to get the lift and the drag, your two quantities of interest. So that's something you do, you'd have to do whether you're using direct or adjoint, so you'd have to do this calculation once, this big one. Now, if you wanted to say, how does that point there affect the lift and the drag? The sort of brute force approach is to say, there's my degree of freedom. Let's see how that affects every single flow variable. And then having calculated every single flow variable, we'll see how that affects the lift and the drag. Now notice there, what you've done is throw away a lot of information. You've said, I've changed one parameter, I've recalculated, say, 10 million degrees of freedom, and then I've thrown away all but 2 of them to calculate the lift and the drag. So what is fundamental to adjoints is that if you do this process I'm describing here, you're throwing away a lot of information. And so if I want to then look at the next point along, the next point along, I'd have to recalculate these 10 million flow variables just to see how that new degree of freedom, that other parameter, affects the lift and the drag. And then if I do the next point, I have to recalculate everything and recalculate the lift and the drag. So this we call this the finite difference approach to seeing how the parameters affect the lift and the drag. And it's very wasteful because at every step you're throwing away a lot of information. An adjoint, on the other hand, does something different. Once you've calculated the flow, which you have to do once, you then say, let's look at the lift and see how it is affected by every flow variable. That's like a partial derivative, dlift by dflow variable across the whole of space. And then see how those flow variables are affected by all of the parameters. That's like chain rule with another partial derivative. And so with a mixture of chain rule and product rule, you get how each parameter affects the lift in just one calculation. And that's a calculation that's very like a CFD calculation, but with slightly different equations. And those equations are called the adjoint equations. And you do the same for the drag. And you'd say, let's see how the drag is affected by every flow variable and see how every flow variable is affected by the parameters. And then in just 2 calculations, you have the influence of all the parameters on the lift and the drag in just 2 calculations instead of having to do it for 100 parameters, 100 calculations. So in any situation where the number of things you can change is very much bigger than the number of things you care about, the adjoint calculation will always be more efficient. And in almost any practical situation, that's the case. You can usually change many more things than the number of things you actually care about. So that's the sort of philosophical approach to adjoints to explain why they are so sort of efficient. And here is an example. It's done, as you can see here, for a Joukowsky airfoil at Reynolds number 400. So this isn't going to trouble any editors of any aerospace magazines. Joukowsky airfoil, I expect many of you know, it's an airfoil that has this sort of shape you see here, but it's defined just by 3 parameters. You have the camber, you have the angle of attack, and you have the thickness. And in this case, we're not going to change the thickness. It'll be fixed constant. So this I gave to an undergraduate to say, you know, in order to understand adjoint methods, why don't you look at this problem? And this is what she created. So if we start off with airfoil 1, that's starting off here with 0 angle of attack and 0 camber. What we do is use the adjoint methods to work out how you would change the angle of attack and the camber in order to increase the lift upon drag. And the lift to drag ratio is what we're trying to maximize here. And so what you get is a gradient at that point. And the gradient says, go in this direction. So we go in that direction. Now, how far you go in that direction is a question for your optimization algorithm. It's a question I won't get into here. But once we get to this point, that's point 2. That's what the airfoil looks like. It's got a bit of camber and it's got a higher angle of attack. So that's, if you like, one iteration. The next one is to say, I'm at that point now. So this airfoil here, number 2. Let's redo the adjoint calculation and work out how to change the camber and the angle of attack in order to increase the lift to drag ratio. So it says, go in this direction. That's increasing the camber and keeping the angle of attack much the same. And that's to airfoil 3. And then you say, right, I'll do the same thing at airfoil 3. And it says you just need to basically slightly increase the angle of attack and decrease the camber. And there's your optimal point. So in 4 iterations, we get to the maximum lift upon drag. All we've calculated is, if the optimization routine is amazing, all we've calculated are these 4 solutions. The optimization routine will probably be calculating a few along the way, just the single direct calculations. But in any case, it's far more efficient than a non-gradient based approach. So what I showed here was a case with just 2 degrees of freedom. Of course, most of the time you'd have hundreds of degrees of freedom that you can change, but just one thing you're interested in, the lift to drag ratio. And this adjoint method really becomes much cheaper compared with finite difference when one has many variables, many parameters, sorry, that you can change. So that was my very simple introduction to adjoint methods. It involved no technical detail, just the philosophy behind it. What I'll do now is talk about how an inkjet printhead works. At this point, I'll mention Tsar, which is a company in Cambridge that makes inkjet printheads. And this project was very loosely done with them. And I was very grateful for the advice that they were able to give me along the way. So very briefly how this works. This is an inkjet printhead nozzle. This is for use in industrial printers, so it's somewhat bigger than the one you might find on your desktop. But you have several hundred channels in this black region here. Each channel sits just here, and I've blown up a channel on the right-hand side. The way it works, ink comes in, it's continually flushed through this channel and out the other side. The flushing is to make sure that any bits of gunk or any air bubbles are continually flushed out. You don't want them getting stuck in the nozzle. At the bottom, that is the face you can see here. At the bottom, there's a nozzle, and that nozzle is typically 20 microns in diameter. It's very small. And then on the opposite face from the nozzle is an actuator. It's a piezoelectric actuator. So you apply an electric signal to the actuator, and it sends an acoustic pulse into the ink that then pushes a droplet out of the nozzle. So I have a little cartoon of that process here. Time on this axis, voltage on that axis. I just put typical times down here. They may not be exactly this. So you start off by pulsing the actuator that pushes the piezoelectric into the ink by just a few nanometers. It's a very small distance. That creates an acoustic pulse here that pushes a droplet out of the nozzle. Now the next stage is often, you could leave it at that and so on. But what you can do also is then pull a piezoelectric element in the other direction to try to kill off the residual oscillations as much as possible. And that's something which we'll be looking at later on in this talk. So that's this bit here. And what I'm going to do in the second part of this talk is just look at this final phase here. This is after we've pushed the ink out, we're going to look at this residual phase, because what we want to do is kill off the residual oscillations as much as possible so that the ink is ready to be pushed out again. If I just pop back 2 slides, down here you can see a typical rate of droplets is 100,000 droplets per second, so 10 microseconds between droplets. And the manufacturers want to increase that rate as much as possible because then they can print faster. But the problem is if you start to eject one droplet or a second droplet before the reverberations from the first droplet have died away, the droplets are no longer uniform. And one thing humans are very good at is spotting non-uniformities in printing. If you can think about reading a book with or seeing a magazine that has a line down it, it's very easy to spot that line. So, you know, the first thing you want is all these droplets to be the same. And the next thing you want is to eject them as quickly as possible. And the way you do that is by making sure that the residual oscillations have died away before you eject the next droplet. Okay, so there's a very brief how an inkjet printhead works. I'll talk about now the governing equations and finite element solver. Anyone who gets lost at this stage, I'll pick you up again in the shape optimization stage. But I think it's important to say a bit about what we did here. So what we'll look at is a 2-dimensional channel. So we're looking at a 2D channel, very generic shape. Real inkjet printheads don't have this exact shape, but this is the one that we were given with to play with because it's so generic. This is the actuator on the top, this is the nozzle underneath. So we consider a 2D channel. We actually developed this so we can look at a 3-dimensional channel that's simply more expensive computationally, and it doesn't change the algorithms. So we developed the algorithms for the 2D channel because it's cheaper computationally. We have a nozzle model here. Now the nozzle has this little sort of hemispherical cap at the bottom. So it's not necessarily hemispherical, it's a spherical cap, which is the little inkjet, and that can go in either direction. You can point up like a meniscus or down like a droplet. And there are actually a few little ways you can model that. And what we did was we constructed a code such that the channel is always modeled in the same way, and you can bolt on a different way to model the nozzle. So if ever there's a better way to model the nozzle, or you want to use different information here, you can just bolt that onto the code afterwards. Anyway, and I think I mentioned this is the actuator that sits above here. So that's the domain we look at. In terms of the equations, they're written here in conservative form. Things to highlight. We have a variable density. I've lost my cursor, there it is. We have a variable density. This is an acoustics problem. So we have the mass, so that's the mass equation with variable density, and it's a conservation of mass, but not a conservation of volume. We have the momentum equation that contains a shear stress tau with, in this case, a Newtonian viscosity. Being Newtonian makes it easier to solve. This whole process would work for non-Newtonian fluids as well, as long as you had a good model for the viscosity. And the energy equation has, of course, that input from the shear stress, but there's also thermal diffusion. And thermal diffusivity is quite important for dissipation of acoustics. I'm in Cambridge today and it's foggy outside, and you'll notice on a foggy day that all the noises get damped. It's harder to hear traffic noise. If someone shouts, you can't hear it so much. And that's because droplets are very good at damping sound. Partly that's to do with the viscous boundary layer around each droplet, but also it's the thermal boundary layer around each droplet. Sound waves, they're pressure waves, density waves, but also temperature waves. And therefore, because you get temperature differences in a sound wave, you get temperature gradients, and then you get thermal conduction across temperature gradients. That leads to an increase in entropy, and any increase in entropy is just another way of saying that mechanical energy has been dissipated into thermal energy. In other words, you've lost mechanical energy, you've damped the acoustics. And that can be very influential. Right, now, okay, so these equations here, you can solve them all in one go. And in many respects, that's the easy way to solve this, but it's not the quick way. The quick way to solve these is to do a low Mach number expansion of those governing equations. Now with that, you start off by saying, let's look at the steady flow. Remember, there's a steady flow going through this inkjet here, which you can't ignore a priori. So let's consider that steady flow. But it is a very slow, I mean, typically I put 1 meter per second. That's a large typical velocity in that sort of printhead. The point being, the Mach number is very small, much less than 1. And then there's the oscillating flow. Now the actuator may be moving over a short period of time, but it's only moving a few nanometers. So the actual speed of that, the particle velocity in the acoustics is also very low, very much less than the Mach number of 1. So with those, you can do a low Mach number expansion of those governing equations. And then that governing equation on the previous slide turns into 3. The first is the 0th order terms, and this is very simple. This is saying that there's a uniform thermodynamic pressure, 1 bar, for example, 1 atmosphere. So we're going to start with the base at 1 bar. You get a temperature distribution once you've got the boundary conditions. This is basically saying del squared T, the Laplacian of the temperature, times kappa is equal to 0. So if you have uniform temperature on the boundaries, then you've got uniform temperature throughout the whole device, the base flow. And then there's obviously an equation of state, which I hadn't mentioned before, but I probably should have done. So that's the sort of 0th order. Then at first order in epsilon, at first order in mu, which is this steady flow Mach number, at first order, you actually have an incompressible flow. So there at first order, your continuity equation becomes conservation of mass, becomes conservation of volume. And then this is a typical Navier-Stokes equation, which you'll recognize. This is the 2 terms here are the acceleration of the fluid, and then these 3 terms here are the forces. So there's the pressure force divided by density here, the viscous forces, and if you want them, the gravitational force. They, of course, are negligible for this problem. So that's the first order terms in mu, and then the first order terms in epsilon. This is the interesting bit. This is the low Mach number oscillating flow. So we have equation for mass, which of course now has fluctuating density because this is the acoustics, momentum, and energy. And an acoustic wave in the absence of dissipation is isentropic. So this is the entropy S, wouldn't change, but because there's dissipation, there is a change in entropy in the system. So there's the first order term in epsilon, and that's the low Mach number oscillating flow, and that's the one that we'll be concentrating on from now on. So what I've done basically with the low Mach number assumption is take the governing equations and reduce them down to essentially two equations, which are much easier and simpler to solve than the original equations together. Okay. Now, how we solve this, we use Phoenix, which is an open source computing platform for solving partial differential equations with the finite element method. I'm a great fan of finite elements. Not only are they arguably the most elegant way to solve CFD problems, but the way they're constructed means that they're very well suited to adjoint calculations. For a bit more detail, that you have test functions in finite elements, and the test functions are the adjoint functions. So if you've never heard of Phoenix, think of it as COMSOL, an open source version of COMSOL, which is also a finite element package. Okay, right, now we're on to sort of how we use the, well, we set up the problem and the governing equations. Now I'll talk about what we did. I'll start with shape optimization. Now this is to say, how are we going to change the shape in order to achieve a particular objective? The objective we'll look at is a decay rate. I have to first of all explain how I get that decay rate. So there we go. So let me go back and forward again. There we go. Right. So what I'm going to do is start off from the governing equations, and I'll write them in a slightly different form. Here I have the momentum equation, the mass equation, and the energy equation. This is for the acoustics. And I'll write them in a sort of matrix form. So I've got d by dt of one matrix A plus B, another matrix, equals 0. So that's just rearranging the acoustics equations, the last of the three that I showed earlier. I have Q, which is a state vector, which contains the velocity, the pressure, and the temperature. And what I'll do now is I'm going to do a separation of the variables. Q is a function of x, space, and time, but I'll separate that down into a function of space and a function of time. And then I'll say that function of time is e to the power of st, where s is a complex number. So it's e to the power s real t times e to the power of imaginary square root of minus 1 imaginary st. So that's what that e to the st is. Now you'll see straight away that s real times t, this is a growth rate. If s real is positive, then this is how quickly these oscillations grow in time. If S real is negative, it's a decay rate. And this SI here is an angular frequency. So what I've done is I sort of hardwired in, I'm just looking for oscillating solutions with a certain growth rate and a certain frequency. And what I do now is I substitute this form here into this equation at the top, and the d by dt terms just become S times the original term. So all the d by dt's have turned into S, which is pops out here. So my governing equation becomes S times A, this matrix, times the function, plus B times the same function equals 0 in the space I'm considering. And that you'll recognize as a matrix eigenvalue problem, a generalized eigenvalue problem. So this can only be solved for certain values of S, and each value of S has a certain function that it corresponds to. So this is a typical solution to a wave equation where we're saying there are certain frequencies and growth rates, and they correspond to certain mode shapes for this device, much as we'd expect. So remember this is what I'll keep coming back to, this growth rate here, because what I'm going to do is say, how can I change that growth rate S by changing the geometry of the system? Now to do that, I'm going to use a technique we developed over the last 5 years, published it in 2019 here, and we also have applied this to cyclonic separators, and that for those of us who, that just means a bagless vacuum cleaner. Anyway, what we have, if we take the flow around a cylinder, this is a nice way to demonstrate this. The flow around a cylinder at Reynolds number 50 is unstable, but you can find the steady solution to the Navier-Stokes equations. Here it is. So the flow goes around the cylinder. I'm just showing the top half, and there's a recirculation zone. Now on top of that base flow, it's unstable. You get an oscillation. And here I'm showing the stream functions of that oscillation and the streamlines with directions on them. And this is the linear oscillation that develops non-linearly into the von Karman vortex street behind a cylinder. So there's the cylinder in this case. So what we do is we say here, if we wanted to change the growth rate or the frequency of this oscillation down here, how can we do so? By changing the shape of the cylinder. And so we're getting the, we'll ask the question, how does the shape here affect the growth rate and frequency of this oscillating mode? This work done by Jack Brewster, who was a PhD student with me who finished about a year ago. If we want to increase the growth rate, we need to push the cylinder up at top and bottom. And of course, the opposite is that if we want to decrease the growth rate, we have to pull the cylinder in, make it more streamlined. If we want to increase the frequency, we actually do something very similar to decreasing the growth rate. We pull the cylinder in. If we want to decrease the frequency, we make the cylinder sort of fatter. It's not quite the same thing as changing the growth rate, but they just happen to be very similar. So we used adjoint methods to get this. So in a single calculation, you work out how to change the eigenvalue by changing the shape, i.e. how to change the growth rate and the frequency by changing the shape of the cylinder. Now that was done with a very quick, very simple, well, I wouldn't say simple, but certainly very quick and cheap adjoint calculation, where the cost function, the thing we were trying to affect, is the eigenvalue, the growth rate and frequency. We can check it against finite difference calculations, which we've done on the right. This is always a good idea. So what I do, if we start off, the black point there is the round cylinder. I'll try and draw a round cylinder. And then we imagine squeezing it top and bottom. It's in the flow moving from left to right. And the adjoint calculation, which is in the open circles, says this is what we expect to happen to the growth rate. The growth rate should decrease. The growth rate should decrease. The frequency should increase, just as we see up here. And indeed, it does that. The black dots show the brute force calculations just by redoing the simulation. And as we hope, their gradients line up at that point, meaning that the adjoint calculation, which gives us the gradient, is giving us the same as the expensive finite different calculations. So we did that for pinching the cylinder up and down, and also for pinching it left, right, which is the red lines. And the main point we see here is that the adjoint calculation on the left here, which is these open circles, completely aligns with the brute force calculation, which are the black dots and the red dots here. So it's a nice little test, and this is the technique we use in this case. So what we do now is we say, I'm going to take, here's my sort of, the flow's coming in here, it's going through this, the shape I showed you before. I'm going to try to change the shape of this device in order to maximize the decay rate, which is actually minus S. Really, that should be the real part of minus S. I'm going to try and maximize the decay rate and make it as negative, make S as negative as possible by changing the shape. Now, if you just leave that, you get a ridiculous answer, which is that it tries to shut this thing off. It tries to basically stop the, it tries to constrict the flow a lot, so that you get a lot of dissipation in the constriction. So you have to give it something to, some constraint, which in this case is an obvious one, which is to say, I want the viscous dissipation for the throughput not to change, or at least not to get any worse. So what I'm going to do now is try to maximize the flows, the oscillating flow's decay rate, while maintaining the steady flow's viscous dissipation. Now, the first time you look at that, you think, is that possible? Because the two mechanisms are both viscous dissipation. So for the oscillating flow, the thing you're going to use to get the decay rate to increase is to increase the viscous dissipation. But you mustn't change the steady flow viscous dissipation. So is it possible? Well, the answer is yes, because if I just go clear the screen, in any oscillating flow, you have nodes, places where the oscillation, there's no motion. And there's a velocity node more or less here. And so you get big, for the acoustic wave, you get big oscillations on the left and the right, and not very much oscillation in the middle. So what you'd expect the algorithm to do, the optimization algorithm with the adjoints, you expect it to constrict around here, where there's a large acoustic oscillation, and then open up in the middle, where the acoustic velocity is small, so you won't change the acoustic dissipation by changing the geometry there very much, but it's making up for the fact that for the throughput, you've constrained the flow here, so increase the viscous dissipation. You need to decrease the viscous dissipation elsewhere to account for that. Now, that's just putting physical intuition. Of course, the optimization algorithm doesn't know any of that, except through the governing equations that you fed it. So it just does what it does. And we start off then with, we parameterize the the shape like this, we give a number of control points and we say to the optimization algorithm, you can move those control points anywhere you like in the 2D plane. And that changes the geometry. And what I'll plot here is a function of iteration number. I'll plot the viscous dissipation for the throughput versus and the viscous dissipation for the oscillation. Now, I won't show every step, but we started off then with that blue and we ended up with a red line, and the red line leads to the same steady flow dissipation as before, with an acoustic dissipation that's 40% higher than it was before. And as expected, it's constricted the flow where the acoustic velocity is largest and increased the gap where it's smallest. I should have said, sorry, because we've got a piezoelectric actuator here, we also constrained the borders here and underneath here not to change shape, so that the only place that they could move up and down, but they had to remain flat. And so we've kept the piezoelectric element here as in a flat region. And we also said you can't change the shape of the nozzle, because unsurprisingly, the thing that changes the acoustics the most is the shape of the nozzle. So this was using the optimization algorithm as a black box. And then afterwards, you can say what's going on. And as I was explaining earlier, you find that the channel pinches where the acoustic velocity is high, the channel opens up where the acoustic velocity is low. So you get most of your acoustic dissipation in this region here. And you also get the throughput viscous dissipation here being high, but conversely, it's lower around here. So this achieves the same throughput viscous dissipation, but a 40% bigger increase in the acoustics dissipation. Now, in a real inkjet printer, of course, there are many other constraints you need to add, many of them for manufacturing. How could you actually make these shapes? So there are many more things to add, but you can add those into the optimization algorithm afterwards. What we've really done here is sort of show that the adjoints are working and can be used in optimization in the absence of any other constraints. Okay, so that was a shape optimization. That's published, I should have said, it's in the Journal of Fluid Mechanics 2019. What I'll do now is talk a bit about actuator waveform optimization. So at the very beginning, I mentioned the actuator waveform. The actuator sits up here, and you can change the voltage that's put onto that actuator. Now, the nice thing about doing that is that you can apply that retrospectively to a channel that's already been built. The problem with the shape optimization is that it may take you a year to redesign a new, to get a new design for a new inkjet. You may not want to change the design. Maybe the only thing you can do is change the actuator waveform, which is a software update. So that's what we'll look at next. Now, in everything I'm going to show you next, we'll just be looking at this left-hand side. So I'm going to assume symmetry, left-right symmetry, and just show you this bit on the left-hand side. So you'll see the nozzle on the right of the image, the actuator, and then this bit here. Slightly annoyingly, you can't quite see what's underneath that microphone sign, but the nozzle sits just there. This is a blow-up of the nozzle. And I'm going to do a slightly sort of unrealistic case, simply because it's a very convenient starting point for demonstration, even if it's not a very convenient starting point for the flow. So I don't quite know what that funny little, let me just try see if I can get rid of that. No, I don't know what that is. We're going to have a funny little A shape. Right. So, right. Okay. So what I'm going to do now is imagine we've started from a case where there's a hemispherical cap or a spherical cap at the end of the droplet here. And in a moment that is going to relax to reach the dashed state there. As it does so, it'll send an acoustic wave into the rest of the channel. And because I'm going to start from the quiescent state in the channel, you'll be able to see that acoustic wave very clearly. So this is what happens if you don't move the actuator. You can see then the acoustic wave moving through the inkjet. Sorry, yes, through the channel. And up here I'm plotting, in the green is the energy within the nozzle, and that's all this surface energy of the droplet here, the meniscus. And the total energy is in blue. And the total energy involves both the nozzle energy and also the acoustic energy running through the system. So that was after 5 microseconds, and you can see that the meniscus decays to its flat state, but there's still quite a lot of acoustic energy left within the channel. In a moment, what we're going to do is see how we can increase the, get this blue line down to 0 within a fixed amount of time by changing the actuator, the mass flow through the actuator, which is modeling the motion of the mass of the actuator through the wall. Right. Now, the way we're going to do that is with adjoint looping. So the way this works is we start off, let's see if my pen is working. Yeah, it is. So we're going to start off at time 0 and do a direct solve. So this is a standard solution of the acoustic equations. So we'll go forward in time until we reach some optimization time after n iterations. So we've just solved the full calculation forward in time. What we do next is we go and do the adjoint calculation backwards in time. And what that does, it goes back through the forward solution. So it's always loading in the forward solution every time. And at every point during that time, it says, how could I change the actuation at that moment in time in order to have the biggest effect on a cost function J, which is what I've drawn up here, which is the acoustic energy in the channel plus the surface energy in the nozzle. There's also the kinetic energy in the nozzle, but that's pretty much negligible. So what I'm doing with the adjoint calculation is at every step along the way, I'm saying, how should I change my actuation in order to have the biggest impact on the acoustic energy in the channel and the surface energy in the nozzle at the endpoint in time. So that's the adjoint calculation. The technical details of that are quite tricky, and I'm not going to talk about them here, but they will be in the paper that, well, they're in the paper we've written on this, which is submitted. So I hope they'll be out soon. But the fundamental point is that you're using this adjoint calculation as a black box to say, how should I change the actuation around here in order to reduce the energy to as little as possible after some fixed optimization time. Now, the optimization time I'll take to start with is 2 microseconds, just here. So what we'll see is, I'll play this a couple of times. Let me go back and forward again. Right. So, okay, I'll just play this first of all, so you know what's coming. Over on the right, you can see here the spherical cap in the nozzle, and watch down here when I press play. The first thing you see, if I go right back to the beginning, the first thing you see is a wave being emitted from the actuator. You see that's the blue thing there. This is pressure we're seeing here. The actuator is moving out, sending out a low pressure wave down towards the nozzle. So this is the surface energy of the nozzle. It's sort of this cap here. It's still high, and then there's a wave heading towards it. And at about this point here, so there we go. About that point there, that wave hits the nozzle and starts to pull fluid out of the nozzle. So now this wave has appeared in the nozzle and it's pulling this cap towards the dashed line. And it does so very quickly. So that wave was set up in order to make this meniscus go back to the dashed line quickly. The problem is, as it does so, it also sends a wave traveling upstream, which is this blue thing here. That travels upstream, reflects off the end there and turns back towards the actuator. And so what the actuator has to do at the end is kill off that traveling wave. So we start off then with what we call the A+ wave. And the A+ wave is there in order to pull the meniscus back towards 0, which it does very effectively. But when it does so, it sends a wave traveling up to this free surface, which then reflects as a positive pressure wave coming back. And then we need to cancel out that wave at the end of the optimization time. So we'll just play it again. You can see there's the wave traveling to the left, bounces off the end, comes back, and is sucked in by the actuator. And at the end of the optimization time, the total energy, the blue line there, has gone to almost 0. It's gone to 5% of its original value by use of the actuator. So that waveform we just seen there was found using the black box, using an optimization method with the adjoint method. No knowledge of the physics at all, except in the way the governing equations are coded in. But you can afterwards interpret it physically. So, and this is the same picture on the left that you've just seen, and on the right, this is the mass flow rate through the actuator So it pulls out. Then there are some wobbles here on the timescale of the height of the channel. They're not terribly important, but the main thing is it cancels out the wave again by pulling out again. Right, so that's one case. The next is to say, let's increase the optimization time to 3 microseconds. And when we do that, we get a very similar behavior, same as before, but now there's actually another wave. You can see it just there behind the first wave, which bounces off and comes back. And what we've done now is, because we have a longer optimization time, the algorithm has found a better way to control this. It's found a better way to suck this meniscus in and return to 0 energy. The way it does it is with one wave that's the same as before, that's followed by another wave. These then reflect off the end and come back, and then it has to cancel the first wave and then cancel the second wave. But that's a better way to get lower energies. And now we've got the total energy down to 0.5% of its original value. So that, again, that was found purely with a black box. So with an optimization algorithm combined with the adjoint methods, but afterwards we can interpret it physically as these two waves. I'll just show the waveform that you get through the actuators. You have the first pulse and then another pulse that's sort of in the opposite direction, a period of nothing much happening, then another pulse, the opposite of the first pulse and the opposite of the second pulse. What I'm showing now is a longer, it's exactly the same as before. Actually, it's a slightly longer actuator, but it's also a longer channel. And for the longer channel, this makes sense. You need to run optimization times for longer, because it takes longer for the waves to reflect off the end and come back. So if I just play this one, we can see now the same thing as before. Big pulse at the beginning. There's actually a second pulse around there. And then you cancel out the first pulse. And then a bit later on, we cancel out the second pulse. And at 5 milliseconds, in fact, even a bit before 5 milliseconds, we've reached the quiescent state. So that's again, using it as a black box. Now, I chose that length deliberately because if we take this left hand here and fold it up, we get exactly the same case as the Inkjet Printhead, which has this sort of L shape in it. The mechanism for the Inkjet Printhead is exactly the same as the one we just saw. The difference is there's a bit of dissipation as the wave goes around the corner. So actually the pulse you get, the waveform you apply, is actually slightly smoother for this case than it is for the straight case, because there's a bit more dissipation around the corner. So once again, after 5 microseconds, we've returned the flow to its quiescent state, but now we've got rid of the spherical cap, and we've done so optimally. So leaving as little acoustic energy as possible in the channel, so that this is ready for the next droplet. And this is the waveform you get. This is the mass flux at the actuator in black as a function of time. And you get a sort of a pulse going in one direction, that's sucking out, and then you push back a little bit. And this is sort of reassuringly similar to the waveforms that they find by trial and error for Inkjet Printheads. By trial and error, I mean performing many experiments and tweaking the waveform to see how to optimally kill off these oscillations between droplets. So finally, I think you can see a lot in this slide. What we have on the bottom axis is the length of the actuator. So we've got a short actuator here, 200 microns long, to a long one, 800 microns. I haven't spoken about that yet, but I'll talk about it now in this chart. Here we have the energy at the end of the time, the normalized final energy. So if we don't do anything, this stays at 1, which is up here. And this is for different optimization times. So 1 microsecond, 2 microseconds, and 3 microseconds. So a few things we can see from this. This is the 1 microsecond. If you say, I want to return the state, I want to minimize the energy at time 1 microsecond, what should I do? The algorithm says, well, there's nothing you can do, because 1 microsecond isn't long enough. So the optimum thing is to do almost nothing if you try to return the state, the inkjet to its original state after 1 microsecond. There simply isn't time to cancel out that returning wave. So the best thing is not to create the wave in the first place. If you say 2 microseconds, I'm going to give you 2 microseconds, you get this A plus A minus pulse, and that works pretty well. It reduces the energy down to about 5% of its original value. But if you say, I'm going to let you have 3 microseconds, then it can reduce the energy to 0.5% of its original value. This is with the double AB pulse. So you found something useful there. The most important thing is to give this, you need to give the actuator time to cancel out the wave it creates. So the wave has to go to the end of the channel and back again, and you need to cancel that wave out. Once you've given it enough time, then 2 microseconds for this particular case is enough, 3 microseconds is better. The next thing you notice is that the actuator needs to be more than 100 microns long. It's got to have enough actuation capability. But once it's 100 microns wide, it doesn't really matter how much longer it is. It doesn't make much difference to the energy at the final time. It perhaps slightly improves in this case as the actuation increases, perhaps slightly gets worse in this case, but it doesn't have a big influence. So there are a few sort of important things to take away there if you were designing an actuator. So that gets me to the conclusions. There's just one slide here for the conclusions. As always, I will leave this up on the screen so you can reflect on it, thinking of questions, but I'll talk through it quickly now. So the main thing is that we've performed this nonlinear adjoint looping, and it's on this viscothermal flow in an inkjet printhead. It's a curious problem because it's a viscothermal acoustic problem. It's quite unusual. And we did that, we wrapped an optimization algorithm around that in order to find the waveform that eliminates these residual oscillations. In the case we looked at, which was slightly contrived for the purpose of presentation, they reduced the energy to around 0.5% of their original value by flattening the meniscus quickly with one pulse and then eliminating the reflected wave with another pulse. So what? Well, I think sort of rather reassuringly, this waveform is similar to that found by trial and error, which by the inkjet printing companies and indeed ones that use inkjet print heads but aren't themselves inkjet printing companies. So what? Well, the minimum optimization time is the time taken for an acoustic wave to travel from the actuator to the open end and back. That's got to be your minimum time between droplets. What next? Well, we've got funding to extend this to 3D. We could, if we wanted to, simulate the exact geometry found in inkjet printheads. That, of course, relies on being allowed to access that. I think this is a key thing, the second point on the what next. I sort of started from the quiescent acoustic state and then did the optimization. Of course, it'd be more realistic to start from the state just after a droplet ejection. And so that's the obvious next thing to do, and then try to return to the quiescent state. And I think finally, the really nice thing about adjoint looping is that you can stabilize or you can achieve anything to any model you have, but you rely on your model being an accurate representation of the real thing you're looking at. Now, the only way to test that is with experiments. And so you really need to run these sorts of simulations alongside experiments in order to work out what the optimal waveform is in practice, not just in theory. So I'll stop there, Jamie. Thank you very much.